Morning, everyone. So over the last two lessons, we took a look at the concept of empirical formula. Empirical formula is the simplest whole number ratios in your compound. Usually the question is worded, we're given a sample, it's analyzed to contain the percent composition of a particular element, a particular species, and our goal was to convert that percentage information back into the simplified ratio for the empirical formula. In yesterday's lesson, we saw empirical formula is nice because it's been simplified. However, sometimes your molecular compounds, especially your covalent compounds, may actually be a multiple of the empirical unit together. So you may actually be double of the Lego block or triple of the Lego block here. We found one easy way to find the actual compound is just to identify the mass. If I happen to be 2 Lego blocks big or 3 Lego blocks big, the corresponding molecular mass would go higher as well. So I'm going to start you off with a quick question on molecular formula, and then today we're going to switch over to take a look at concentration. So we'll just do this as a quick warm-up here. So what we're told in this question here is we have 2.476 grams of an oxide of copper contains 2.199 grams of copper. Question here is determine the molecular formula, determine the actual compound, given molecular mass. Now they're going to come up with a lot of names for sort of mass, things like that. So this is like molar mass, but it's molar mass of your molecular formula. Given the molecular mass is 286. And remember, for masses, it's best to say no units because it's relative to carbon. So that's the question as worded here. I'd encourage you just to pause the video, see how you do with it. Assuming that you've done that, we can take a look at the answer here. What I would do first is I would start off trying to dissect this problem here, convert the word problem into either balanced equations or pictures if I can. We're given 2.476 grams, so sitting in front of me is a total sample, 2.476 grams. We're told it is an oxide of copper, meaning it's a compound that's made out of part copper and part oxygen. You'll notice I put the metal first. What we're interested in first is the empirical formula. I want to know CuXOY. I want to know what's the ratio between Cu and O represented if 2.199 grams is actually copper. Like we mentioned yesterday, it may not necessarily be all the copper on one side, but just for easy drawing, I'm just going to put them all on this side here. The other side here is definitely oxygen. Remember, we're going to put just a single O because this is not oxygen by itself. It's actually being stabilized by the copper. If I know that the total mass is 2.476, I can subtract off the 2.199. That should leave me with how much left over is oxide. This only contains copper and oxygen. So the remainder, what's left over, is this many grams of oxygen. You could hypothetically go back to percentage, but the whole point of doing percentage was to get to these masses anyways. So we already have these masses, we're ready to go. What we're going to do here, this part is very systematic. You're going to set up a row. What do we know about the copper? Well, it's 2.199 grams. What we know about oxygen currently is 0.277 grams. What we're going to do is we're going to divide out the molar mass. So double check my numbers here. Make sure you're using your IB periodic table. So they have 2 decimal places, 63.55. Single oxygen weighs 16. So let's see what that gives us here. I'm dividing out their own molar mass to convert to moles, and that way I have a number that I can actually compare between the two. We can be a little sloppy with sig figs here because eventually it's going to round to 1 sig fig anyways, and definitely I don't want to accumulate any rounding errors. So this is 0.0173. If you're keeping track of your units here, that's actually moles. So technically I could say Cu 0.03 to oxygen 0.01. Just to start making it look nicer, our step was let's divide out the smallest one. In this case here, the smallest one is 0.0173. And in this case here, practically 0.0346 divided by this answer here, I'm getting 1.9998 for the copper, and the other one definitely knocks to 1. Remember, as a general rule, you're going to use your judgment here. I don't want to do any crazy rounding for one chemical, or else it's going to skew the proportions. In this case here, 1.998 here, no one would complain to you, well, it's basically 2 there. So far what we've found is based on these numbers here, based on the percentages that are represented in these numbers, the empirical formula is Cu2 oxygen 1. Now this sort of makes sense here because as an ionic compound here, Cu is actually in that transition metal section, it can be multivalent. Most common charges are +1 and +2. In this case, by finding the empirical formula, I actually know, okay, the ratio we have is actually the copper 1 oxide. However, we're still interested in finding this molecular mass here. Let's take this empirical formula. Assuming this is our compound, let's find what our empirical mass is. It's like doing molar mass on this Cu2O. Again, you normally don't show this work, but what we're going to do is we're going to take twice the mass of copper. Copper earlier we said 62.55. I added to the oxygen. What we're saying here is just the Lego block itself, how much does it weigh? This one weighs 143.1. Again, best to say no units. That is called your empirical mass because it is the molar mass of your empirical formula. And now what they tell you is when they went to test the actual compound, the actual number of building blocks together, the whole compound weighs 286. If you want to do that with the formula, you can say, well, how many Lego pieces would I need? What we're doing here is we're taking the molecular mass, we're taking the actual mass of the compound as given. You do whatever you can to get grams per mole, and you divide out the empirical mass, you divide out the mass of the Lego piece, and basically figure out what that ratio is. In this case here, we know that the top number is 286. If the empirical mass is 143, give or take, this one here is going to be give or take 2. At this point here, it really should be a whole number. It shouldn't be a 2.5, and I need to still rescale it because the molecular mass should be some multiple of your empirical unit. So multiple of your empirical unit. And basically our real compound then, it's double this. So I have 2 of these Lego pieces together. That means I have Cu4O2. A little bit strange, especially when we talk about ionic compounds. Usually ionic compounds we say, well, they're lattices. They repeat anyways. So if the ratio is 4:2, why don't I just bother writing 2:1? There are some places that these ionic compounds actually exist as minerals. And in that case there, it may actually be a slightly larger grouping than we're expecting for the lattice. This one here would form, again, I don't know exactly how things are bonded, but it may actually have, well, 4 Cus somehow bonded together along with 2 oxygens, and they may end up forming what's called a dimer together. I know the ratio, you're correct, it's 2:1, but maybe it's almost existing like a covalent compound where they're actually always 2 together. And then we have maybe next to it on the lattice, maybe another copy of this, maybe another copy of this. So therefore, maybe the building block of it is our molecular formula based on our question, Cu4O2. So make sure you practice your worksheet so that you're comfortable doing empirical formula, molecular formula. You're going to find comparing to the question that we did yesterday. It's not as hard because we didn't need to do the extra work to actually find how much carbon and how much hydrogen in a burning reaction. But this part here, they would expect you, once you have those percentages, you know how to divide out the mass, divide out the smallest one, and definitely scale it up in case I have multiples of your empirical unit. For today, we're going to switch gears here, and we're going to switch to another conversion. That was sort of our detour, a little bit of break from our mole diagram. So we're going to look into a field of chemistry here called solution chemistry. Solutions here, if you remember from our physical matter notes here, a solution was a homogeneous mixture. It was a mixture that was so fully dissolved that it felt like one material altogether. In this case here, we're going to look at solutions that are made primarily dissolving solids into liquids. We're going to revisit terms like solubility, low solubility like we saw earlier. Hypothetically, you could actually make solutions, say, bubbling gas into liquid as well, but we're going to just focus on dissolving solids that are solid into a solvent that's a liquid. So, in order to make this solution here, what we start off with here is a background. You can assume that the background, we're going to call this the solvent. We're going to assume that the solvent itself is water unless otherwise told. So what is a solution? A solution here is a homogeneous mixture. It feels like one material. It's a homogeneous mixture made by dissolving, here's some terminology for us here, we're going to dissolve a solute. So solute is usually the solid. It's usually the thing that's currently here in lesser quantity. And we're going to dissolve it into the solvent. And as I mentioned here, the solvent, this is the thing that's in greater quantity. If you actually look at the density of water here, the solvent is way higher concentration. So solvent, the greater amount here, and we're going to always assume this one here is water. And therefore, when things get dissolved into here, therefore we can then use the terminology of aqueous because they've been fully dissolved. So what we're going to do is we're going to start off with just maybe a beaker of water there. I'm going to have some solute. Let's say it's table salt, NaCl. No trouble having table salt here in the solid form, right? Even though you memorize alkali ionic compounds here should be fully soluble. Until you drop it in water, it can stay solid, no problem. But in this case here, my table salt here, I'm going to assume I'm not tossing in as much table salt as there are water molecules. As I drop this in, sure, we want to check our solubility chart in tomorrow's lesson here, but basically what I want to do is I want to dissolve this table salt here. Does table salt dissolve in water? Of course it does, because we end up getting really salty seawater here. And in this case here, we'll have another look later on with what did the water actually do to the table salt. But at least in this beaker here, we can now label the table salt as being aqueous. What we're going to do here is we're going to switch over to a quick simulation just to get you familiar with what is a solution. I'm going to introduce you to the notion of a concentration, and then we'll come back and we'll practice some of the questions here. Okay, so I pulled up a quick simulation here. You're going to find a link to this here under the resources section. As we just talked about here, we start off with a beaker of water. Currently what they're showing you here is 1 liter's worth of water. What we can do here, we can actually toggle the different chemicals. We'll pretend we're making some juice of some sort with the drink mix here. I have a handy concentration meter. That's going to be our conversion factor for today's lesson here. Normally, concentration here, it needs to be specific for a particular chemical. I don't have meters that detect every single ion, but there are a few ions. For example, a pH meter will sample the acidity, so sample the H+. If it's a colored solution, maybe I have a concentration meter tell me how much molarity the color is. In this case here, this is ideal. This is the concentration of how much drink is in the solution. I want you to focus on the units here because this right here looks at moles per liter. It says, pretend I have a whole liter, how many moles would I have? What you'll notice here is inside my container is not quite a liter. I'm still going to scale it up. 1 liter happens to be a convenient comparison unit. So I'm going to picture, well, so far I haven't dissolved any drink mix. So far the concentration is 0. As I steadily drop in the drink mix, more of this is going to dissolve. I'm going to just do this shaker here. As I drop more and more powder in, it's actually giving me how many moles have been dissolved. Sure, sitting in front of me was just dissolved per half liter, but they've scaled it up here. Well, if I had a full liter of exactly this juice, it would be 0.23. Well, given only half a liter, although the concentration is the same here, I would know I only have half the number of moles. Half the number of moles and half the volume will still give me this intensive quantity here. Per liter, I have equivalent of 0.23. What's going to happen to this concentration as I drop in more drink mix? Well, as long as I don't change the pool size, all that's going to happen is I'm going to dissolve more. This concentration here will steadily get higher. Again, you'll notice concentration always has it per liter. I haven't changed the size of the container at all. So sitting inside my beaker here, maybe only 0.205 moles, sitting in half a liter. If I pretended I had a liter full of this solution here, that's what concentration tells me. It gives me a nice conversion factor between volume as well as moles. So steadily here, you can just increase concentration pretty easily. Just dissolve more powder. Usually when you do a lab, they actually call for a certain concentration to make sure there's enough chemicals to actually collide. You want to be really careful when you're trying to do this dissolving. Normally you would weigh out the solid, add in a liquid afterwards, just in case the solid actually takes some room. But let's say this experiment here called for a very particular concentration. Let's say I would need a 1 molar solution, 1 mole per liter. So what I'm going to do here is I notice, oh, I'm not high enough here. I'm going to steadily increase my drink mix, my shaker here. I'm getting close, so I want to add it a little bit slower. And then let's say I shake it a little bit too hard. Whoops. Oh no, it's now a little bit over. In this case here, because those solids here are going to be fully submerged and fully dispersed in the solution, there's no way for you to take a pair of tweezers and grab that drink powder back out. So in this case here, normally you need to start over. Oh, my concentration is too high. There is a solution, however. How can we knock this concentration here lower? If I wanted 1 molar, but right now I have it too high, I can try thinking about, let me dump out the solution here. If I dump out the solution, surely the concentration would drop, right? Well, let's have a look at this number. Currently is 1.120. As I dump out the solution, the pool definitely goes down, but you'll notice, wait a second, this concentration meter here actually didn't change. Because what's actually happening here is as I turn on the tap, you are definitely dumping out powder, but you're also dumping out water at exactly the same rate. So in that case there, again, I have less and less volume in the pool itself, but since concentration says pretend I have a whole liter of it, because the powder and the liquid is going out at the same rate here, overall my concentration actually doesn't change. So that actually doesn't help. I could, in this case here, the solution to actually knock this concentration down, I imagine the moles of particles as little particulates, little solids here. I know they're fully dissolved, but they're sort of like swimmers in this swimming pool here. What I can do is I can, instead of adding more swimmers, instead of adding more drink mix, what I can do is I can just increase the pool size. by increasing the pool size, I have the same number of swimmers. Great, they have more room to actually swim in. I want you to notice what happens to this concentration as I just add pure water, just from the tap on top here. If it will let me, there you go. So I'm going to add in some water here, and you'll notice steadily that concentration goes downwards. If you're looking really closely, you'll actually find that the coloration, the color intensity actually drops as well. If it's the chemicals of the drink mix that actually make you colored, and now I have the same number of swimmers, but I have a much bigger pool to actually be colored into, the color intensity definitely drops, and therefore, again, assuming we have a full liter of it, I expect the concentration will be 0.279. There's one other thing I can do to this here is I can deal with an evaporation. Evaporation was one of our separation techniques using the fact that things boil at different temperatures. I would always assume that ionic compounds, given their lattice structures here, they boil really high. So we're going to assume that the water boils off first. What's going to happen to this concentration as I put this on a hot plate here, as I increase the heat and actually evaporate the solvent, but leave the swimmers behind? Hopefully you're able to say to me here, well, the concentration here should steadily increase then, because all I'm doing is I'm doing the opposite. I'm removing the pool, I'm removing the water, but all the swimmers are behind, and basically I am increasing the concentration. So that is another way to change the concentration. I could have it so much so that I increase it so much that there actually is no water left over. That's why the concentration meter is complaining. Well, you don't have a solution anymore. And what you have left is little crystals of the drink mix actually powdering out again. In that case there, you may have seen the term saturated right before this happened. A saturated solution we'll revisit tomorrow. Basically, it's containing the maximum amount of dissolved solute. It can't handle dissolving anymore. There's no gaps left behind between the liquid molecules that are slipping and sliding past each other. And we'll deal with it in tomorrow's lesson. So that's what I want to introduce to you as concentration. When you play around with the simulation here, you can play around with different chemicals. They chose many different color solutions, and you can also play around with what if I dump more chemical in, what if I add water, what if I evaporate it, what if I remove the solute somehow, if I can, because in this virtual environment, I can just remove the powder. You have to always think in real life here, because the solution will be so fully dissolved, you can't easily do that removing. So let's flip back over to our notes here. All right, so our main term for today's lesson here is concentration. This is going to become another useful conversion factor for us. Concentration, by definition, it describes the amount of solute, how much salt did I dissolve into a given liter of solution. So amount of solute per given volume of solution. So it dissolves how much is dissolved and how big the pool is. I'm going to give you three very common units for concentration. So for concentration, you can actually express it expressed as, first way here, most natural, even outside of chemistry class, when we're making drink mix here, what we want to express it as here is actually express it in grams per liter. Because normally I don't know exactly what the composition of the drink mix is. I don't know the molar mass or anything like that. But I can just put it on a kitchen scale here, measure out, okay, I have 5 grams here. Again, liter was just a convenient unit for us to compare. Remember in that simulation that we did, we didn't need to have a full liter of solution. It just says pretend I have a liter of the exact same concentration. How many moles would be sitting inside there? So in this case here, grams per liter. So I have G per L like this. Again, IB doesn't like using liters, so we're going to go gram per decimeter cubed, dm cubed. And in this case here, sometimes, especially when things are in the denominator, I can actually write it grams is fine. That's on the top. This dm per dm cubed like this, I can actually write that as dm to the negative 3, and that negative 3 just means per dm cubed. So gram per liter, really common unit for concentration. That's actually going to tell me how much drink mix I've actually dissolved per liter. Now, in the chemistry context here, if we happen to know what the chemical is and we happen to know the molar mass, maybe it might be convenient to actually use moles per liter instead, right? Because we saw moles, it's like a box full, it's a Avogadro number inside. If I can actually find the moles, I can actually do some neat stoichiometry in next week's lessons. So let's figure out here for moles per liter. In regular grade 11, grade 12, we would now call this the molarity of the solution. The molarity tells me the number of moles per liter. The molarity would have molarity with units. We're going to call the unit here molar, and we're actually going to use capital M for it. So far, we would say moles for a given liter. When they say per liter, they mean per 1 liter. In regular Chem 11, Chem 12, they would summarize this as capital M. Again, IB doesn't like using this liter here, so let's see what they'll write it as here. Mole per dm cubed, like we said, so mole per dm3 like that. And then again with the per, we can go mole dm to the negative 3. So IB will, where in regular grade 11, grade 12, it's really simple just to say, oh, how many molar solution? They'll actually put the number, but they'll put this mole per dm cubed in that fashion. Let's make sure we understand what this number is. Let's say I have an acid, and my acid is quoted at 1.5 molar HCl. Concentration is an intensive quantity. It doesn't actually depend on how much is present. So intensive does not depend on amount. So even though this concentration conversion, 1.5 molar, this one here means 1.5 moles for a given liter, that doesn't mean sitting in front of me has to be a full liter. But what it does say here is if I have a liter. So for every 1 liter, there should be 1.5 moles worth of, and the chemical right beside it is what they're giving you here. That means I have dissolved in, there are 1.5 moles of HCl per 1 liter of solution. And you'll notice I've changed the language a little bit here. We made a solution by dissolving solute into solvent. Technically speaking, the solute particles will actually have some volume. It will increase the solvent's volume by a little bit, but usually it's so minimal that we just assume that pretty much whatever solvent volume that you have, the solute basically fills in the holes left behind by the liquid slipping and sliding past each other. The whole volume of the solution, even though it might be a smidgen higher, practically doesn't change. So there we go. We have 1.5 moles HCl per 1 liter solution. I mentioned it was intensive. What if sitting in front of me, like our simulation, what if we only had a half liter? Well, how many moles would I expect in there? Not 1.5 moles. In this case here, if I have half the volume, I would have half the number of moles. If I have 0.75 moles, right, less solution here means I have less chemical inside. But what you're going to find is if I divide 0.75 by 0.5, I'm going to still end up with the same concentration as 1.5 molar. So concentration is a nice conversion factor for solutions. It says pretend I have a liter of whatever solution you have. I don't care what volume you have. But if I had a liter, this is how many moles you would find inside. Now, how do we interconvert between these two units here? We started off with grams per liter. That's sort of like kitchen chemistry. You would put it on a kitchen balance and actually measure the masses. What we want to get to is moles per liter. So a lot more useful as a unit we're going to see later on. Well, let's just set up our unit conversions here. Let's set up a fraction. The unit I want to get rid of is grams. The unit I want to pick up is moles. Have we seen this conversion before? A conversion that converts you between grams to moles. Hopefully you're able to say to me, well, this is just molar mass. So depending on the chemical, you can look up the PhET, the periodic table, add up the bits that make up this compound, and this molar mass, in this case here, gram per liter divided by molar mass, because molar mass would actually be down here, divided would give you mole per liter, or you can multiply the molar mass and get back to gram per liter. So you can always convert gram per liter to mole per liter, assuming you know the chemical, assuming you know the molar mass. There is one other unit that we typically use here, and this guy here is called parts per million. By extension, you could do parts per billion, parts per trillion. In this case here, parts per million is ppm. The way I want you to think about this basically just sets up a ratio. It's essentially exactly the way we set up percentage. So let's take a look at a fraction here. Let's take a number 2 over 3, right? So 2 over 3, we don't like fractions in chemistry here because it looks exact. I'm going to write it out as a decimal just so that I can represent more sig figs. Well, 0.67 here isn't that tiny a number. But what do we do here is if I say, well, let's multiply it by 100 so that I can get a per cent, right? Cent is 100. If I pretended to have 100 squares in front of me and I color in 0.67 of those squares, well, that means by percentage, I've colored in 67% of those squares. And what you see has happened is I arbitrarily scaled it out to 100 because 100 was convenient for me. And what it's done is it's taken a number that's tiny like 0.67 and made the number look a little bit nicer like 67. For parts per million, it is exactly this. It's just that this decimal is so tiny that even if you did percent, it's still going to be 0.000, lots of zeros. What we're going to need to scale it up by, instead of percent, which is out of 100, I'm going to scale it up by a million, or if it's part of a billion, scale it up by a billion. I'm basically rescaling, pretending I have this many squares, this many grids in front of me. If I scale it up by this million, how much do I actually have? So this is definitely useful in dealing with numbers that are super tiny. I'm going to set up the ratio for you here. Our parts per million, that's going to be sort of this percentage here. Our parts per million is basically a ratio between the mass of solute, so how much solid material divided by the mass of the solution. So it's a mass per mass sort of ratio. And in this case here, my scaling factor is not only 100, because it's parts per million, I'm going to scale it up by a million. The numbers I'm looking at are so tiny that I need to multiply by such a huge number to start getting slightly better readings. We use this a lot when we're testing sort of water quality. I might figure out what's the concentration of heavy metals in your solution here. Let's say, just as an example for this one, we don't use this unit too much, but I just want to make sure you're comfortable with it. Let's say I stick my meter here into the water. Again, it's intensive, so it doesn't matter the pool of water. But if I know the size of the pool of water, I can actually do a few calculations. Let's say my meter reads here, I have 5 parts per million of lead concentration. So heavy metal lead, I don't want this in solution. Even though I know the number is tiny, even if it increases a little bit, it can cause a lot of health problems. I have a 5 parts per million, that's what my meter is reading. And let's say what I'm testing here, 5 parts per million of lead in a 2.5 liter sample. It was totally up to you how much of a pool size you would be testing. If you have more volume, you would imagine there's more particles inside. But remember, concentration is just that ratio. It's how much solute is per given solution. So let's say it rated 5 parts per million in a 2.5 liter sample. What I want you to do here is calculate the mass of lead 2 ion present inside this 2.5 liters. So again, what I want to emphasize here is for all concentration, regardless of what the unit, it doesn't mean that you have to have 1 liter. In this case here, I actually have 2.5 liters. When I stick my parts per million probe in there, it tells me, it senses that in this 2.5 liters, there is actually 5 parts per million of lead. That's what my meter says. All you're going to do is you're just going to match it up to the formula. I'm going to put the parts per million on the left side. My parts per million is going to be the mass of solute. That's what I want. How much mass of solute, how many grams of lead 2 plus, divided by the mass of the solution. I would need to find out how much mass is 2.5 liters. Again, because we can assume that this is water, water is nice. The density of water is 1 gram per milliliter. And therefore, you can convert that here. That's 1 kilogram per liter. So basically, when it has liters, it's actually telling me it's going to be 1,000 grams. So if I have 2.5 liters, that would be 2,500 milliliters, and therefore this one here would be 2,500 grams worth of water. Again, that is just the water's mass. It doesn't include the lead's mass just yet. But again, I'm going to assume that the lead is so fully dissolved in the water, practically the 2,500 dominates over whatever grams of lead I happen to be able to dissolve. Remember, the scaling factor here is actually being multiplied up by a million. I'm scaling it up by quite a lot. And just a little bit of algebra for us here. 5 times 2,500, I get divide over the million. And in this case here, I'm getting, well, how many grams of lead are inside literally this 2.5 liters? There are 0.0125 grams. Like 12.5 milligrams, right? It's a fraction of lead here. I needed quite a substantial amount of water to actually make this number fairly large. But you see, writing a number like 5.0, the unit here would be ppm. Writing a number 5 would be easier than writing a number like 0.0125. All right, so that's just practice using that last unit here. We're going to go back to look at the more common units, so gram per liter and moles per liter, and we're going to do a few conversions there. So a new example here, usually they're going to word it in this fashion here. What is, they're going to introduce to you a square bracket. Square bracket actually implies here, what is the concentration of, and then usually they tell you the chemical inside. What is the chemical? Well, in this case here, the chemical is NaCl. So how many moles per liter of table salt did I dissolve in the mixture when? Let's dissolve in here 0.15 moles. That's how much table salt is dissolved into 125 milliliters. So let me just draw a quick picture of this. So sitting in front of you, again, is nowhere near a liter. I only have 125 milliliters. You're going to see a lot in this section here. Most of our conversions are going to be moles per liter. Very quickly, you're just going to do in your head here, well, I know 1,000 milliliters make up a liter, so I'm going to convert this to 0.125 liters. I only have a fraction of a liter right now. And what I'm doing here is that started off as just pure water. I start off with 0.15 moles. They've already helped you out a little bit here. This is not a kitchen scale. This is not a grams just yet. They've already done the molar mass for you. But you happen to know this is 0.15 moles. The chemical is NaCl. You drop this powder here into the mix. You can assume this one here is alkali salt. It's fully dissolved. I just want to know basically how salty this water is. What's the concentration in this solution? If you look back at your definition, we've been saying concentration, I'm going to put C. It describes how much solute. Earlier we said it could have been mass per volume. In this case here, because I want it in concentration, I'm actually going to want to quote it as how many moles. For some reason, we're going to use N for moles. So N is actually the number of swimmers expressed as moles, which is 0.15 this time, but it's expressed per volume of solution. In the end, I want it per 1 liter, but it happens in this case here, I actually don't have a full liter yet. Only after you do the division, it rescales it. Pretend I have a whole liter of it. How many moles would actually be inside? So that's a formula you can look at here. This is straight from the definition. Concentration is moles per volume. So let's figure out here concentration. I literally dissolved 0.15 moles. I dissolved it into our 125 milliliters. I want to convert this to liters because if you look at our units up above, it was either gram per liter or mole per liter. By doing this division here, 0.15 divided by 0.125, I'm getting the concentration. You'll still need to do your sig figs. The concentration here is now 1.2 moles for every given liter. In regular grade 11, grade 12, you can even write your answer like this, 1.2 capital M like that. In words, you would say 1.2 molar. This says, pretend I have a full liter, which I know I don't. If I had a full liter of it, there are 1.2 moles. In this case here, I only have an eighth of a liter. So in this case here, I only have an eighth of the 1.2. So concentration is intensive. This now becomes a really useful conversion factor because this can get us between a volume of solution and how many moles. Once I'm back at moles, I can just jump around my diagram again. So I'm just going to give you the summary map here and leave you with one last question. Again, as you're learning this here, it might be nice just to draw the summary map a couple times. Hopefully, eventually, you'll just have this memorized. We started introducing the mole concept. The mole is a box. Inside is an Avogadro number. To convert moles to a number of particles, Avogadro's constant was 6.02 times 10 to the 23. Make sure you memorize that number. Yes, we did that strange. What if it's a molecule and an atom? I'm not going to do that detail right now. We can convert, depending on what's actually in your chemical, I can convert it over to a mass bubble. Every chemical has a different molar mass, so you actually need to look at your periodic table and you just add up the different bits and pieces. Earlier, we had done a bubble going over to volume. But there was a restriction on this volume bubble here. It had to only be for gases. Gases are really wildly separated. They really respond drastically to temperature and pressure. And you can assume that we're at a standard temperature and pressure. We'll come back in a later lesson to talk about what if we're not. In that case, there, the conversion factor was called molar volume. 1 mole is equal to 22.7. Again, IB doesn't like liters. They would rather say decimeter cube. And here we are. We're introducing one last bubble. And this bubble here is actually going to also be volume. But this one here is specifically going to be volume of a solution. When I actually dissolve solid into liquid, this conversion factor will always change. The conversion factor will be based on the concentration. Based on the strength, based on the taste of the orange juice at that moment here, based on that molarity, gets you back to moles, and then eventually you can go to mass. So let me just leave you with this question here. We'll practice a very similar question in tomorrow's lesson as well. Let's say, what mass of CuCl2 is needed to make 250 milliliters. So that's going to be a cup. 250 milliliters of 1.50 molar solution. As you start looking at this question here, we'll just sort of liken it to things that we've done before. So we've been asked questions before. Well, let's calculate the mass. Right? We find it on our table here. I want to eventually get there. The reason why this way of showing it here is a little bit harder is, oh no, I actually have two numbers. I always tell people to start off with the easier of the two numbers. In this case here, I would say, well, 250 milliliters, that's going to be volume. Well, am I volume of solution? Am I volume of gas? In this case here, they tell me that I'm a solution. That means I'm actually starting over here. Meaning, do not use 22.7. We're not a gas in this case here. This 1.50 m is actually our concentration. I would say this number here is harder to work with because that capital M here is actually molarity. That capital M actually hides inside of it moles per liter. So that actually is a conversion factor for us. So what I would do here is I would start off with volume, because it's just the 250 milliliters. Sure, I might need to convert to liters. Use this concentration 1.5, get it over to moles, and then use your periodic table, figure out how many grams per mole, and go from there. You could totally do the concentration formula just by itself. You can say concentration C is equal to N over V. Well, we're interested in N is equal to C times V. We're going to use that a little bit more in tomorrow's lesson. But for us, especially as we look into stoichiometry next week here, we're going to find that these conversions here happen one after the other. I don't want to accumulate rounding errors. What you can do is you can do this all in one long row. Start off with the volume, which is easier, although I'm going to convert this here to 0.25 liters. When you do your conversion, you want to make sure your sig figs are still correct. 250 is 2 sig figs, so this is still 2 sig figs. 0.25 liters. Well, I want to get rid of liters and go to moles. That's going to be my first conversion. And my second conversion will go from moles over to grams, which is mass, moles over to grams. So again, I can see it's going to be a 2-step conversion based on my map here. Do not use 22.7. So don't use 22.7 decimeter cube because we are not a gas. Instead, what we're going to use is the concentration. Concentration says, well, pretend for every 1 liter, when there's a 1 with the L, there actually are 1.50. Do I actually have a liter? No, I only have a quarter of a liter. But by doing this multiplication, I figured out how many moles are just in my quarter liter because I knew the strength of the orange juice so far. I'll leave this for you here. Look up the molar mass of copper chloride. So add up this mass here. That number here will go up with the grams. Numbers on top you multiply, on the bottom you divide out, and then eventually you'll have your final answer in grams. We'll practice another one of these in tomorrow's lesson and finish off solution chemistry tomorrow. Thanks, guys.